Hello, everyone. My name is Jesse, and I'll be your MC for today. Today, we have a wonderful speaker by the name of Shreya Shankar. Shreya is a computer scientist living in San Francisco, interested in making machine learning work in the real world. She's an incoming Ph.D. student at UC Berkeley. Previously, she was the first ML engineer at the Viaduct, did ML research at Google Brain, and completed a Bachelor of Science and Master of Science in Computer Science at Stanford University. Today, the title of her talk is Catch Me If You Can, Keeping Up with ML Models in Production. As a quick reminder to the audience, we will be posting some questions in the polls. Please fill in the session polls and type your questions in the chat so that I can ask it to Shreya at the end of this. Now, please, Shreya, without further ado, take it away.
Thanks, Jesse, for the lovely introduction. Hi, everyone. Super excited to be here. I hope that this talk is super interactive, so please post questions, I think, in the session chat or something, and I'll get to them whenever, so feel free to interrupt. But yeah, today I'll be talking about ML models in production and the challenges around keeping them there even when you deploy a model. So let me get started. A little bit about myself. I did my undergrad and master's at Stanford CS, and I also did research in machine learning there. And then I joined an applied ML startup as the first ML engineer, with the goal to learn kind of how do we apply our ML methods that we've learned through research in industry. And I did a lot of things at Viaduct. I worked with a lot of data. I did a lot of engineering and infrastructure work. And I guess anybody who's worked at a startup knows that your responsibilities kind of span a lot of different verticals, right? Recruiting, engineering, ML, product, and more. And through my time there, I learned a lot of things. A big thing was that academic and industry ML efforts were very different. When I was doing ML research, I focused a lot on training techniques. And if I did care about robustness, it was in the form of fairness metrics or generalizability to test sets with unknown distributions. I also did research in adversarial examples, but I found that the problems that I was working with on a day-to-day basis when I joined a startup were very different. We wanted to, at the bottom line, train few models, but do lots of inference with these models and make sure that they work every single day or every single time that they're run. And this motivates a key question, or this motivated a key question for me, which motivated me to go back to grad school. But what happens beyond the validation set or the test set? In academia, right, we work with these fixed train sets and test sets, and we show high performance by saying, hey, like this model does well on a holdout set. But as many people who have probably deployed models in production settings in industry, you could have a high validation set metric and then deploy your model and experience degradation for some reason. So this talk is mainly not about the feature engineering or data science, but kind of what are the challenges. And so there's kind of a depressing truth about ML IRL, I would think. Many data science projects don't quite make it to production, and this could be for many reasons, right? One big one being quote unquote real world data is not necessarily clean and balanced like our canonical benchmark data sets. Maybe like ImageNet is a good example of that. Data also, quote unquote, in the real world is also changing, especially if you are working with time series data. And showing high performance on a fixed validation set doesn't quite mean you're going to have consistent high performance when you've deployed that model. So as I mentioned before, today's talk is not about training algorithms or feature engineering or data science. I will talk a little bit about some of the challenges that I have faced post-deployment of models, and I'm sure other people resonate with this, and also challenges my friends have faced. And I will also talk a little bit about what I'm working on in my first year as a PhD student, a coarse-grained lineage and tracing tool for end-to-end pipelines. So let's jump into some of the challenges that we face whenever we are working with end-to-end ML pipelines. One big one, I think, is data lag. And there are many types of this kind of lag. two of them are feature and label lag. So you could imagine feature lag is our system only learns about the raw data or experiences the feature transformations well after the raw data has been produced. We can also get label lag. So maybe our system only learns about the label well after the features have come in. So one example of this is maybe I'm Uber or I'm a ride sharing company. I'm trying to predict whether a user will give a high tip or not. Maybe I find out about the ride information in real time, but then I only find out about what tip was given after the payment has gone through. And so why is lag bad, right? Or why is it bad to have these inconsistent timings of when data comes in? A big reason is that the evaluation metric is inherently lagging, which means that you can't have your model reflect the most recent data that has come in. And in practice, like especially if you're working with time series data, right, it can be very hard to make sure your model is having high performance or performance in real time that's matching that of the validation set. Another big challenge that a lot of people talk about and we see like on a day-to-day basis, right, is distribution shift. So data quote unquote drifts over time, and of course models or various components in the pipeline will need to be retrained to reflect such drift. So a big question here, right, is how often do you retrain the model? And the underlying question for that is when has the data shifted? But you could also say like, okay, like maybe you can just imagine like the data shifts all the time. As soon as time moves on, like we could retrain our model. So why don't we just retrain models as much as we can? So there are several reasons, right? One is that you just get added complexity to your overall system. So every time you retrain a model, you have more artifacts to version and keep track of. Every time you run a training job, right, model binaries are produced, metrics are produced, you have to store them somewhere. You have to be able to efficiently query them in some registry. You have to promote it to the production workflow. All of this can make things more complex. Retraining can also be expensive in terms of compute, especially if you're like trying to train deep learning models. Every time you train like a large NLP model, right, you can spend anywhere between like hundreds of dollars to like thousands. I mean, the state of the art models are, I don't know, cost like millions of dollars. And another one that I think isn't talked about very much, but retraining really does take time and energy from people. Every time a new model is trained and promoted to production for a specific task, there's more information that needs to be shared with the people who are directly responsible for that task. And it makes it much harder, right, to onboard a data scientist onto that task, especially because a lot of these workflows can be run and then you have no idea how to store all of the information about these runs in one place. So how do you know when the data has drifted? If you want to just retrain when the data has drifted. And a common thing that people do, right, is monitor their models in production. And what do we monitor is another big question that varies by task and by team. In the words of the agile philosophy, right, you want to monitor proactively as much as possible. And this can be especially hard when there aren't labels coming in real time, or you're getting some form of label lag. So for a first pass monitoring, I've done in the past, like monitoring your model output distributions or your prediction distributions, monitoring averages and percentiles of values. And then we've gotten to the point at my previous company where we were monitoring the feature distributions or input distributions, monitoring distributions of data at every step of the ETL processes. But this can get really, really tedious if you have many features or steps in your ETL pipeline. And one great example of this is a lot of companies have this kitchen sink approach of feature generation and model training, where they just generate like thousands of features and store them in a feature store or feature table, and just fit a model to all of those features. And so if you're going to monitor the distributions for each one of those features, right, who wants to look at a table of at least thousands of statistics and then figure out if that's different from last week's data or so forth. And even then, right, when you have monitored all of these metrics, and you're somehow able to look at a dashboard with like thousands of columns in there, how do you quantify the change? How do you know if the mean feature value has deviated significantly from last week's mean feature value, for example? How do you detect that? And then how do you act on this? This is also super big open question. And I'll talk a little bit about how traditional data monitoring techniques have failed for me in the past, and maybe this might resonate. But I remember tracking mean and variance for a task, and that can work in some cases, but it also fails in many situations. For example, if you're looking at distributions of multiple modes, if your skew and kurtosis change, for example, the mean might stay similar, but your actual distribution has changed. So one other option, to be a little bit more complicated, is to run statistical tests on all of your features. So imagine for a statistical test, you're running like a Jensen-Shannon divergence or a KS test. But these tests in practice can have a high false positive rate. And especially if you are working with very large data sets, or you're working with, I don't know, thousands of predictions or so forth. In my experience, yes, this method has flagged distributions as significantly different when the distribution has changed, but it's also flagged distributions as different even when the ML metric doesn't really change very much, or the accuracy or whatever I'm trying to measure. So that's kind of tedious. You can get alert fatigue, and the era of big data, right? We're working with large amounts of values. P-values specifically are not very useful to look at. You can just have a very small p-value from a statistical test, even just by virtue of the fact that you have so many data points. And one other thing I could mention in this slide is you could look at the test statistic, like the KS test statistic, or the actual value of the Jensen-Shannon divergence. But then it becomes hard to determine, like, what does a test statistic of 2.1 actually mean in practice? Like, how does that relate to the feature values? You need a data scientist who's done a lot of exploratory data analysis and is familiar with the data in order to tell, like, whether that's actually a meaningful change in the data, which also makes it hard to bring new data scientists onto the team. So a very unsatisfying answer to how do you know when the data has drifted, I think, is you just don't, or at least we're at a point in time where we don't really know, especially if we're working with large and complex distributions. Time series data is a great example of this, and a lot of people work on time series ML problems. So an unsatisfying solution, right, is just to retrain the model to be as fresh as possible. I know, like, big companies retrain and deploy thousands of times a day, especially working with recommender systems and so forth. So, okay, imagine you're trying to retrain your model to be as fresh as possible. What kinds of bugs will surface when you are continually training models? And I have a few here, and I'm sure people have run into a lot more. But there are a lot of ML bugs you could have in production, right? One being the data has changed or been corrupted. Let's say like a sensor value, or sorry, a sensor on a specific vehicle, if we're using the ride sharing analogy, now has snow all over it. So now you can't get good values from it, but you have no idea. You could also have data dependency or infra issues. So maybe if your upstream data source is like a Snowflake table and your Snowflake ingestion job failed, that could be an issue. There's logical errors that I've seen all over the place. I've made tons of them. Like I've joined two tables on keys that can have null values in tables. So that's bad behavior. I've seen logical errors in retraining the model, promoting the wrong model to inference. I've seen it and I've done it. So there's a lot of this. There's also there can be changes in consumer behavior, like events could happen, COVID could happen. We have no idea how people interact with the outputs, and it's very hard to really directly measure that. And there's many, many more, of course. But why are these bugs like significantly different from bugs that you might face in software engineering pipelines? A big one is that the ML code fails silently a lot of the times. Like you'll have few runtime or compiler errors. And one example of this, right, is the bad join that you might have. You can almost always get a join to work if your tables have the same column names, or you've specified your join keys. But does that mean your, I don't know, data outputs are exactly what you expect them to be? We don't know. There's also very little or no unit or integration testing in feature engineering and ML code. And it's not to say that people are bad software engineers or anything. I just think it's very hard to actually figure out what are the correct tests to write, or integration tests, unit or integration tests to write when you are constructing these data transformations. Another big one is that very few, if any, people have end-to-end visibility on an ML pipeline. So on an end-to-end pipeline, you could have people from like infra engineers, data engineers, ML engineers, data scientists, whoever's deploying, like the QA people or DevOps people. Yeah, it's just very hard for one person to just know every single step in your end-to-end pipeline. So how can you go and trace back your bugs to responsible components? I think this also motivates something that I've noticed, is that we're kind of at an age in the field where we could use a lot better monitoring and tracing tools for these specific tasks. And there are so many artifacts that we have to keep track of when we are doing these things, especially if you retrain your models. A lot of companies also have pipelines that have multiple models chained together. And so having these dependencies also makes it more complex. So when we do retrain regularly, even if we have monitoring solutions, of course, we could, what I've done in the past, and I've given a longer version of this talk at the Databricks conference recently, but we could have some sort of infrastructure that, like a model registry, to keep track of which model is the best model. Or we could manage the versioning and registry ourselves, and that inference time, right, you just pull the best model from your model registry. And then maybe you could do a forward pass through your pipeline and come up with a prediction. But in a lot of cases, right, when you do have these bugs, then the question becomes, how do you go and act on the bug? If a client reports that this is a bad prediction, how do you go and figure out what steps were actually involved in making that prediction, especially when you have these forms of lag? A client could get back to you in like 2 to 3 weeks saying, hey, this is wrong. But by that time, maybe like all of your steps in your production pipeline have been different. So the first PhD project that I've kind of worked on is a tracing tool for these complex data pipelines, which I will describe and hopefully demo. Yeah, we have enough time, so that's cool. So I built mltrace pretty recently, and it's still very actively under development. But the idea here is that we want to be able to trace data as it flows throughout these complex pipelines. And it's designed specifically for pipelines that have many steps, like cleaning or feature generation or training or whatnot, that have different owners. And so teams that are pretty multidisciplinary. Currently, the first release has a Python API to log information about the runs and a UI to query those logs and view traces for outputs. I see a question about the slides. The slides are on my GitHub, and it'll be at the end of this talk. I'll show you the link to the. But going back to the talk, yeah. So some of the design principles, whenever I build the first release, or that I care a lot about simplicity. If we're just having some sort of logging mechanism and a mechanism to query these logs in ways that ML practitioners would want, the tool needs to be really, really simple. There isn't, the user doesn't really have to manually set component dependencies in the pipeline. The tool resolves them once the user specifies the IO. And the API is, in theory, designed for both engineers and data scientists. As someone who has worked pretty extensively in both kinds of roles, definitely is room for tools that cater to larger groups of people. And the UI is designed for people to help triage issues, even if they didn't build the components themselves. This is useful because imagine you have a PM that's received news about a bug. When there's a bug, whose backlog do you put it on? you don't really know unless you can kind of trace back to the steps that were involved in making that prediction. And this makes it easier, right? Like if you can have multiple people on call for a specific task, because now people who might not have developed the model could investigate the bug. Some concepts for the specific tool are similar to Dagster and TFX, if people are familiar with that, but pipelines are made of components. So for example, we might have like cleaning components, feature generation, train test split, inference, whatnot. And the key here is that different artifacts are produced when the same component is run more than once. So different data sets are produced and whatnot. So the two abstractions we have are components, as I mentioned before, and then component runs, which are instances of that component being run with the version code, the version inputs and outputs, the dependencies that are resolved through the tool and whatnot. There's two ways to do this logging. There's a decorator interface that's very similar to Dagster, the solids, if people have used that. And there's also a alternative Pythonic interface that's similar to MLflow tracking. So you just create your metadata that you want to log and call a function to log it, and then you can use the UI or the CLI to query those logs. So the integration example is pretty straightforward. Let's say you have a function that cleans your data, takes in some inputs, has an output. To use mltrace, you just add your decorator, which specifies the name, the variables that represent the inputs, and the variables that represent the outputs. So let's say here, their inputs are the raw data file name, and the outputs are whatever path of the output. Right now, the IO is basically string identifiers. It was just simple to build that way, but there's somebody actively working on other integrations, so hopefully we can make more progress there. So when you decorate the function, and then every time you run it, the logs are stored to a database. Let me switch to the next slide. And it's essentially a Python API. You run your functions as you would usually. So let me show a little bit about the UI. So here's like a toy pipeline example where like I'm running inference on the New York. I'm running inference for a task where the task is to predict whether a rider will give a high tip or not. And the data set here is the New York City taxi cab data set. So you can see here, like the last thing I ever ran was an inference, and I can maybe trace the output to see all of the steps that were involved in producing this output. So you can see, like, even in such a toy pipeline, it's pretty complex. This inference depends on feature generation and training, where feature generation depends on this cleaning stage. The train stage depends on, or produce this model depends on other features, which also depends on like a train test split and whatnot. So you can see that it could get pretty complex, and it's there's a lot of information here. And then one of the things we recently added to the tool was staleness indicators. So we track two types of very basic staleness. One is, can I increase font? Yes, I can. I hope this is better. So we track two types of staleness, one being a component in the dependency list was run a long time ago in terms of absolute time. Like the user can manually set this threshold, right? The default is 30 days, but let's say your model is more than a month old or something. If you're trying to run inference with that model, you will get this kind of alert. There's another type of staleness that we track, which is you promoted the wrong component version to production pipelines. So this is just saying that there are 9 fresher versions of that feature, and maybe we used the wrong features. We don't know. But this kind of error is less likely to happen if you have like more robust infrastructure, if you're using like MLflow model registry, or if you're versioning your data properly, which is also hard. But I've seen this error happen before, and I've definitely run into it many times, so that's what motivated it. Okay. let me move back to the slides. So that's kind of where it's at right now, but there's still some work to be done. I think this is just a first step, having a trace. The next thing you want is to be able to flag outputs and figure out like, okay, where do we go and start when we want to debug something that's wrong? Like what components should we look into first? And that's definitely on the roadmap. So we have several things on the roadmap. Right now, the only logging can be done kind of through Python, but we have gRPC integrations on the roadmap. Also Prometheus integrations for monitoring the output values, as I mentioned before. Monitoring is definitely important, but it's definitely hard to do. Right now, someone's working on a DVC integration to version the data. So that way we don't have to deal with only these string identifiers and not be able to check out the versions of data that were created at those points in time. Also ML flow integrations, specifically with the model registry. But the thing I'm most excited about right now is an ability to do some sort of causal analysis. Like if you flag outputs as mispredicted, the tool should be able to find the component runs that were common between those outputs and hint like maybe you should look into this component first with this code and these data versions that came in and out. Another thing that people have been interested in is lineage at the record or row level. And it's vague, but essentially they want a way for any identifier in the outputs, flag all of the rows in all of the tables that are required to produce that output. So that seems like more of an interesting technical problem on the roadmap, still actively thinking about it. So just to recap, we talked about several things, a lot of challenges around continuously retraining models and maintaining ML production pipelines. I also introduced kind of what I've been working on recently and plan to work on for the next several months, but a tool for coarse grained lineage and tracing. And there are a lot more, I think, areas of opportunity in this field. I did not even touch any of the problems around deep learning, but there's a lot more around there. Like, for example, if you use embeddings from deep learning models as features to downstream models, how do you track those dependencies? If somebody updates the deep learning model, then all of the data scientists downstream need to be notified, which can be hard. Another thing is that specifically with deep learning, a lot of models are heavily over-parameterized. So it can be kind of hard to know or figure out what behaviors to expect at runtime. Another big one is around collaboration. I think it's how do you enable anyone to build a dashboard or monitor a pipeline? And here, right, the ML people or the data scientists know what to monitor, but the infra people, they work with Prometheus or CloudWatch or whatnot on a regular basis, and they know how to monitor. So how do you build tools that allow engineers and data scientists to be more self-sufficient? So there's a lot of things. And I have all of the links here. I know people have asked in the chat, essentially, but the code for this talk, the toy ML pipeline, which I didn't go over here. It's in a longer version of this talk, but you can kind of see examples of how to integrate mltrace. Yes, mltrace is available right now for you, so please check it out. Let me know what you think. Super open to feedback. And if you have any other questions or comments, you can email me first name, last name at berkeley.edu. And thank you. This was super fun.
Great. Wonderful. Thank you very much, Shreya. So if we have any questions in the audience, please feel free to write it down. We got one. So Victor asked, what alternatives to mltrace have you seen?
Yeah, I really modeled it off of things like Sentry or observability tools that you see in infrastructure. So you can definitely adapt those tools to ML workflows, but again, I think it's one of those things that it requires somebody who's super familiar with infra and engineering, as well as somebody who's familiar with the ML wants and needs to be able to merge the two. So.
Thank you. Right, just ask if you have any thoughts on how to do ML as part of the agile team.
I think, yeah, it's a good question. It's a very broad broad question, but one of the issues that I had faced in the past, especially when I first started doing like data science work as a day-to-day basis, was that people did not align on the terminology. So like not everybody was familiar with what a metric meant. Like maybe I said, not everyone knew like precision or recall or F1 or all of these technical terms. So really, I think the first step on an agile team is to make sure like every single person understands exactly what the metric is and how that metric is created and how that derives business value. And then it becomes a little bit easier to divide up the work.
Great. Thank you for that answer. As a follow-up, Rajiv asked, do all the tools still require a data scientist to get the best use out of them, or can a QA engineer, for example, use them?
To all the tools, just in general, like in like MLOps, or I'm going to imagine that's what it was. Yeah, I think the question, I don't know how to answer this well, but I would say that the issue with making QA engineers doing all the testing is that testing is very specific to the transformations in ML. So maybe that's like the model, that's some of the ETL that a QA engineer might not be super deeply familiar with. So that's what makes it hard for QA engineers to use ML specific tools. That being said, I'm sure like we are going to move to a place in which people are more self-sufficient. I don't know what that's going to look like, but I think it's pretty exciting.
Makes sense. All right. So if we do not have any other questions in the chats, well, thank you very much, Shreya, for your talk. That was really learned quite a lot in such a short time. And yeah, I wish everybody an enjoyable rest of the events. And if you have any other questions, please feel free to reach out in the chat or directly to Shreya with her email address. Thank you very much.
Perfect. Thanks so much for having me.